Hello, everyone. So today we're going to look at a topic that's, deceptively uh, easy. But the point is that this topic, the cardiac cycle, which is one of the main topics in the cardiovascular physiology, is so ridiculously easy. And it's very easy to understand and, reproduce on the paper. But most of us uh, we mess up some place or the other. It may be in our understanding of the topic, it may be in the simple differences or the nuances in the mechanical contraction of the heart, or whatever reason there are. But this topic, even though it's quite easy, is one of the most important topics we're going to learn. Why? Because A, it's going to create your whole understanding of circulation, but B, more importantly, as side of a student, there's a lot of exam questions. I mean a lot. The practical paper, it can be the theory paper, the MCQs. Every examiner's favorite topic is this one. So today we're going to try to build like a simple understanding of the topic. Of course, if you go through the actual books and the medical resources, then you are going to find a lot of information on these topics. And I really do want you to go into those and, make this a much better, much more polished topic of yours because trust me, you're going to need it, right? But here we're trying to at least understand it somewhat as much as I can teach you. But here we go. So, in the general characteristics of the cardiac cycle, first of all, you have to understand the heart works as two separate pumps, right? There's the left side, there's the right side. Both have the atria and the ventricles. The atria are the, squishy top part, and the ventricles are the much bigger, thicker, lower parts, right? So, what is the definition of cardiac cycle? Like, if you want the bookish definition, like you should just look it up because that will make a lot more sense. But just to understand, it's basically the series of events that happen in the heart from one heartbeat to the next, right? That's the time frame we're working with. So, the atria primer pump is actually um, a term that's used quite a lot. So we have to understand what exactly is a primer pump. A primer pump basically means that it's going to prime the ventricles. What do you mean by priming the ventricles? It's going to give or pump the blood into the ventricles so that the ventricles can then pump it through the rest of the circulation. That's the pulmonary and the systemic circulation. That's the basic idea and the understanding behind atria primer pumps, right? Now, the diastole and systole. These topics we're familiar with, all through our 11th and 12th. But, you come into medicine and there's all these new terms and these new ways you can understand the same thing. So it's really important and it's really interesting too. So what is a diastole? I think everyone knows this. It's basically when the heart is relaxing. So there can be atrial systole is when the atria is contracting. Atrial diastole is when it's relaxing. Ventricular systole, diastole, same thing. Joint diastole is when both of them are doing nothing, right? They're just relaxing, chilling by the beach, right? Now, what's a Wiggers diagram? Wiggers diagram is a very important diagram. You need to know this. And I have it here somewhere. Yeah. This one is a Wiggers diagram. And I don't really like how it's explained in the book. So I'm going to try to explain it in my own words as best as I can. But the basic idea is that the Wiggers diagram is going to encompassate everything that's happening in the heart and show it to you in a graphical format with pressure and volume, right? So here you can see the pressure and the volume is given, and these all stuff we'll come to in a minute. So these dotted lines that you see, going through here and then, coming here, this is the aortic pressure. So the pressure in the aorta throughout the various events. We'll talk about these events, but I just want you to understand what the various things are. The red line, that's the ventricular pressure, and the dotted line that kind of coincides with it is the atrial pressure, right? So these two are the main things that people ask questions in. Apart from that, we have the ventricular volume, which corresponds to the various events which I am going to talk about, and I'll explain them in relation to this so you understand it better. This is simply the electrocardiogram. I will make a video on the ECG separately because it's like a really big topic and I really want a lot of time to explain it. To explain it in one video it's just not efficient. And this one is just a phonocardiogram, which is the heart sounds, which we will also talk about. So these are basically the things in the Wiggers diagram. I want you to keep this diagram open or in your mind when I'm going through the stuff, and you have to relate how the various curves are changing, because I will come back to this at the end, right? Okay, so this was the Wiggers diagram. So now think about this. The normal duration of the cycle is 0.833 seconds. What happens if you increase the heart rate? Someone told you to run a marathon, you know, what happens then? Well, this the thing is, the heart's going to be contracting really fast. So what do you think is going to contract, is going to be exercised more, the systole or the diastole? The systole, right? So the systolic part of the whole cycle will be more dominant. So like normally systole is just zero point 0.4 fraction of the cycle duration. But when the heart rate's increasing, like it's almost 3 times, the systole part may even take over 0.65 fraction of the cycle duration. So that's a lot, that's quite a big jump. And the diastole decreases, right? Because the heart doesn't have time to relax. That's why you get tired, because the blood flow is not going in the normal fashion. The heart is not being able to pump as much blood. So, blood is accumulating, then there's lactic acid production. That's a whole different sector. But that's basically why you get tired, right? So the mechanical events is the main crux of the whole thing. So I've been making this flow chart throughout my first year. And yeah, it's not the best flow chart if you want to replicate this in an exam. The better flow chart would be to just, go through the whole page. But, for understanding, this is perfect. So it's just split into ventricular filling, which is basically the diastole or the joint diastole, where no one's actually doing anything. So imagine the ventricle has just contracted, right? It has contracted, now it's relaxed. So now what happens? Whatever happens is happening in the diastole, and what is going to happen? So imagine the atrioventricular valves are closed, right? And the ventricle is just relaxed. So these are going to open, but the thing is, the atria also have had, blood coming in through the vena cava, the superior and inferior vena cava, or the the pulmonary veins, whichever side of the heart you're talking about. But they have blood, right? So what do you think is going to happen if this relaxes, this opens, and suddenly the blood that was here, it's it's going to drop, right? So in the first third of the ventricular filling stage, it's known as the rapid filling stage, because all that blood is just going to drop, right? You can do it at home if you want to, take like a bottle, a cup, make a hole through it, put a bowl under it. You can try to do it. Uh, yeah, so first third is going to be very fast. Second one third is going to be kind of lazy, that the blood is coming through the veins whenever it wants, and it's going straight to the ventricles. Okay, it's pretty chill. Last one third is the atrial systole, where it's going to actually the atria are going to contract, and they're going to push the blood into the ventricle. So this actually accounts for a 20% increase. So people who have some dysfunction in the atria, they might not even notice it, because 20% is not really a lot. If you think about it, it's only going to matter if you're doing some, like a very high exercise, or like a very exhausting thing that you're doing, maybe running from murder or something. I don't know what you guys get up to, but yeah, so then your atria is not going to work. That remaining 20% is going to make you tired much quicker, and that will cause arrhythmias and stuff, right? So now let's go into the isometric contraction, right? This is the systole, right? The ventricular systole. So basically, the systole is split into two parts. the isometric contraction and the ejection. Ejection we'll talk about in a minute, but isometric contraction. Isometric basically means it's of the same size. Now you're going to think, okay, it's contracting. It can't be the same size, right? It just can't. It's contracting. No, it's contracting, but the blood isn't going anywhere. Why? So the semilunar valves, they're closing. If we're talking about, say, the left side of the heart, then the left ventricle is, trying to pump, but the semilunar valves are closed. Why are they closed? Because the pressure in the atria, or in the aorta, is going to be more, right? So whatever pressure the left ventricles have, when they're contracting, until they reach the minimum pressure of the aorta, the valve is just not going to open because of, well, simple physics. There's not really a lot to it. In caveman language, ooga booga, ventricular pressure less, aorta pressure big, valve no open, right? But the ventricles contract, the pressure increases. The second it goes over the minimum pressure, which is basically the diastolic pressure, which is going to be 80 mmHg, so the blood is going to pump out, right? The blood is going straight out, right? So duration of this is about, I think, 0.02 to 0.03 seconds. Not really a lot. Now we come to the ejection part. So 60% of the volume of the ventricles is going to be ejected. Out of that, 70% is in the first third, and the next 2/3 is about the remaining, that is 30% of the 60%. So 18% of the whole ventricles, right? So yeah, this is basically it. If something's contracting, the valves are open, blood is rushing into the aorta. Isovolumetric relaxation. So iso volumic or isometric, whichever one you want to call it, means the same thing. Uh, so basically what happens is that ventricles are now, they're going to relax. But, you know, there is going to be some change, right? There has to be some change. So in the body, what happens is that everything is not instantaneous. Even though the ventricles are relaxed, so they don't have as much pressure, so valves would just shut. Some tiny amount, tiny amount of blood is going to go right back into the ventricles before the valves can shut, because the body is imperfect. It's not some machine that can do it instantaneously. So this small amount of blood is the protodiastole, right? And the duration of this relaxation is, I think, about 0.03 to 0.06 seconds. Now we go into the electrical events of the heart. I'm not going to go over it too much. I want to make a separate video over the whole ECG of the heart, which is the electrocardiogram. So basically there's the P wave, the QRS complex, and the T wave. Now the P wave is because of the atrial depolarization, right? The atria are going to contract. They need some sort of depolarization, yes? That's the P wave. The QRS complex is the ventricular depolarization. And the T wave is just the ventricular repolarization. And please keep in mind that we're saying T wave is the ventricular repolarization. So a lot of time people ask, what happened to the atria? Did they just disappear? Do they not get repolarized? No, they do get repolarized. It's just that since we're measuring it and the T wave is much more dominant because the ventricles are big, right? They're gonna cause a bigger wave. So they're just going to overshadow the atrial repolarization. So that's why. It's a very famous fiber question actually. The pressure changes. Now the pressure changes, I can just show you in the Wickers diagram. So you see these in the atrial pressure part. See this A, the C, and the V. These are the pressure changes that will take place. So the A wave is taking place during the atrial systole, right? Atria is contracting, it causes some change in pressure, yes? The C part is taking place during the isovolumetric relaxation. Yes, you can just check it out there. And basically the V part is going to just be here, just at the end during the ventricular contraction, like near the end of it. So that's just the pressure changes in the atrium. No one really asks this too much, and it's not really that important. Maybe it is important later on, but for me, as of right now, it's just something you should know. The aortic pressure curve. Now, aortic pressure curve, again, it's just going to be here. So remember how I said AT, MM, AG, the valves are going to open. So the aortic valve is opening here, like right after the isovolumetric contraction. So it contracted, it's going to go here. It just shoots up, right? It shot up. And the reason why it shot up is basically because the aortic valve, once it opens, the rapid ejection phase is going to start. So it's the aortic pressure is going to change very quickly and very fast. But then it's going to slow down. Then the valve closes and it's going to go right back down. Then again, it's going to repeat. So see this protodiastole part during the isovolumic relaxation. So this is known as the incisura. It's also a pretty famous question that people say. Um, yeah, and that's about, yeah, C incisura. Now the hard sounds are these ones. So I think everyone knows this, but I'm going to talk about it anyway. This is because of the first one is because of the atrioventricular valves closing. Second one is due to the semilunar valves. The third hard sound is basically because of the atrial systole, and the fourth one is because of the gushing of the rapid filling phase of the atria, right? Yeah, that's basically it about the hard sounds. Then let's look at the graphical analysis of the pumping. So graphical analysis of the pumping is basically like a pressure versus volume diagram. So pressure versus volume diagram is quite simply just, well, we've all gone through 11th and 12th. We know that pressure versus volume curve is usually used to find the work done by a system. So these are the phases, phase one, phase two, phase three, phase four. Uh, I've just drawn this very quickly so that, you can understand the phases. And I'm going to explain the phases here, right? So the end systolic volume is the starting point. Yes. So everything, there was a systole, right? The volume is going to be at minimum in the ventricles. So the pressure in the pressure doesn't really increase, but there is going to be the filling thing, right? Because of diastole. So the volume goes up to its maximum part. So diastole done. So this is the end diastolic volume. You just relate everything. So the mitral valve closes, yes? Now everything contracts. Pressure is going to shoot up, but the volume remains the same. Why? Because isovolumetric contraction. Isovolumetric, no change in volume. Aortic volume valve opens. This is again the period of ejection. Uh, the way we talked about it before, that this part is a little bit steep because of the rapid ejection, and this part is kind of because it's pretty slow later on. Again, the valve closes. This becomes isovolumetric relaxation. Yes. So that's about it. Oh, okay. Efficiency of cardiac contraction. Very important. Kind of forgot about it, but yeah, it's pretty important. Basically, what is it? What is the efficiency? The efficiency of cardiac contraction is basically the amount of the fraction of the work done by the heart that is actually used to pump the blood, because most of it is going to be just used as heat energy. So the normal efficiency is pretty high actually for a machine. Well, for a human organ, I'm considering it to be a machine. It's about 20 to 25%, so it's pretty high. A person with heart failure, on the other hand, well, yeah, the whole point is that the musculature is going to deteriorate. So the fraction, if the total thing is going to go down, also the efficiency also declines. So it's pretty bad. So it's around 5 to 7%. So not only heart failure, actually, I've written heart failure here, but if I'm being honest, like it's not just heart failure, it's like any kind of di some dysfunction of the cardiac musculature due to some genetic problems, or there can be some traumatic injury, whatever the reason, right? It will cause this failure. So this is basically all about the cardiac cycle. Uh, it's not really that hard, nor is it like, you know, some huge thing. So I think it's the way I've explained it, it should be pretty self-explanatory, most of it. But you should definitely go through the reference books and everything. But yeah, this is the second video. I hope everyone enjoyed, and tell me in the comments if I missed anything, if you want clarification of something, maybe something I went wrong somewhere, because this is all one take. I'm not going to edit it. I'm doing this in my free time. I have to do an insane amount of work after this. And yeah, it's not fun. Being a medical student is not fun. It's anything but fun. But yeah, please like the video, do the YouTube stuff, whatever it is, and yeah, thank you so much for your time. Thank you. See you next time. Yeah.